I hit the start.
Yeah, I can see in the status bar.
Okay. Wow, it's like doing this little like percentage thing. It says I am live now.
You are live. Go for it.
All right.
Although we've got, actually, it's a minute before 10, so you probably want to give it a few seconds.
Oh yeah, I'll wait before I like go into my presentation. Wait for the audience to gather. Let's see. I can't accurately see the attendees, can I?
No, we cannot see who's here.
Getting it a couple more. We're just like 50 minutes in, or 50 seconds in. Good morning, welcome. Hey, Mervin. Hi, Lisa. Give it another minute here. Some more people come in, introduce themselves. Morning, Mercedes. Melissa. Jerry. Good morning. I think I'll go ahead and start now. So good morning, everyone. My name is Darold Wallick. I'm a technology enthusiast and an avid DIYer. I work for the Paul Banner Mission Indians in the environmental department. I'm in charge of the air quality monitoring program. And I want to thank you all for joining my session. I'm going to try and not bore anyone. And I've added some fun stuff to the presentation, so bear with it. Let's go ahead and get started here. So, from the first slide, I bet you can tell what some of these items have in common. And if you guessed DC electricity from batteries, that's correct. But more importantly, these all carry batteries that use a lithium chemistry. And lithium is an element that can be found on the periodic table of elements. It has the atomic number 3. The Li symbol is what it's seen as in its abbreviation. It is the lightest and least dense of all pure elemental metals, which is like a tongue twister there. But the compound's been used in several different industry applications. It's used in the making of heat-resistant glass and ceramics, lithium grease lubricants, flux additives for iron, steel, and aluminum production, and batteries. Today, lithium batteries are used everywhere, as you can see in the picture. And the reason why I wanted to discuss this is...
Hold on a second, Darold. We're not seeing your slides, so I think you might need to switch screens.
Uh-oh. Hold on here. Let's see here. Sorry. Can you guys see that?
Yes, now we can see them. All right, go for it.
Holy smokes, I'm sorry. Give me a second here. I gotta pull up my control screen here.
See, this is what happens when you're fancy and you have two screens.
I know, right? I'm sorry. That's what I get for being a techie geek. So let me continue on with our presentation. You guys can see it all right and hear me okay?
Yes.
Okay, perfect. So continuing on, I'm going to share a few facts that you may not know about lithium. Uh, First one is it's uh, it's found in trace amounts in our human chemistry, which is kind of interesting. Along with its other uses, it's widely used in small concentrations to treat manic depression, hyperactivity, and other mental disorders. Um, because it's so reactive and quick to oxidize, it is only found in minerals that contain lithium that has bonded with other metals. Um, and last but not least, lithium is so highly volatile, lithium batteries can and will explode if you handle them improperly. And this is the main reason for the presentation. So I'll give you a brief battery timeline here, some history, and some people that may have gone unrecognized for their accomplishments. So here we go here. Try not to bore you. So back in 1786, Luigi Galvani is an Italian physicist. He kind of paved the way for the battery. He was dissecting a frog, and he was using a brass hook with an iron scalpel. And when he touched the frog's leg, it twitched. And so he thought this was due to animal electricity, which later Alessandro Volta, another Italian physicist, believed the phenomenon was caused by two dissimilar metals and a humid conductor. So Volta later verified this through experimentation. And in 1800, Volta took his research further by making the first wet cell battery, known as the Volta pile. And it's basically consisted of layers of copper and zinc divided by layers of cardboard and cloth soaked in brine. Um, it was the first true battery producing a stable, consistent current. After this, there were many other discoveries leading up to the first rechargeable battery. This was discovered by Gaston Plante and improved by French chemist and engineer Camille Alphonse Faure. I hope I'm pronouncing his name right. But the batteries produced before 1959 were referred to as primary batteries or non-rechargeable. The lead acid battery was the first rechargeable battery using a wet cell. Um, like I said, the previous voltaic pile was a wet cell and it was a one-time use battery. And Faure's improvements helped the battery perform much better than the original. So this was pretty cool. First look at rechargeables, and they're still used today in our cars. George Leclanché, another French scientist, took a wet cell electrolyte of ammonium and chloride and created a paste that led to the first dry cell rechargeable battery, which is they're still using dry cells today. Like when you go to the store, those are pretty much dry cells. 200 years or 20 years later, Carl Gassner, a German scientist, took the Leclanché battery by adding the mixture of plaster of Paris and a small amount of zinc chloride. The mixture allowed for a longer shelf life, and then he obtained a U.S. patent in 1887, which paved the way for the first mass-centric batteries powering portable electrical devices. Then there was, I kind of went too far here, sorry. Yeah, so this was Ernst Valdemar Uner, which was a Swedish engineer. And I don't know if you guys ever heard the chemistry NiCad. It's a combination of nickel and cadmium in the electrodes, and they use a potassium hydroxide solution, which is lye if you make soap. It was the very first battery to make use of alkaline electrolyte, giving it better energy density that led to more energy density than lead acid battery. And then later, when we got into the 1900s, there was a American physical chemist, Gilbert Newton Lewis, who experimented with lithium. But it wasn't until later that it became commercially available. In the 70s, We had Michael Stanley Whittingham. He was a British American chemist. He's a key figure in the history and development of lithium ion batteries. He discovered the concept of intercalation electrodes. And the term intercalation refers to the process whereby a guest molecule or ion is inserted into a host lattice. The structure of a guest host or intercalation compound is only slightly perturbed by the host structure and the reaction used to form the compound and is reversible. So yeah, intercalation is just another term for being able to insert between layers in chemistry. But after he successfully did this, it was another American material scientist and solid state physicist, John Bannister Goodenough, who was able to take Dr. Whittingham's work and improve on it gratefully by changing things around to lithium cobalt oxide, which is a lightweight, high energy density cathode material, and it doubled the capacity of the original lithium ion battery. Oops, jumping ahead here too fast. Later on, a Moroccan scientist named Rashid Yazami, he was developing graphite electrodes, or the anode, which is the negative pole of the battery, and using a electrochemical cell that had a polymer electrolyte. And this is actually still used today in our batteries, the graphite anodes, and it's like a $80 billion market. After that, Akira Yoshino, a Japanese chemist and professor, created the first safe production viable lithium ion battery, which became widely used in cell phones and notebook computers. Sorry, this is a lot of stuff, but I hope you guys are like not falling asleep on me. And then later, another person who is the senior vice president and chief technology officer of Sony, Yoshio Nishi. He headed the team in development of the first commercial lithium batteries, and in 1991, his team succeeded in the commercialization of the first lithium-ion secondary battery. Secondary meaning it's rechargeable. So yeah, that was a whole mouthful. The cool thing is that these guys were, four of them right here were recognized in 2014 for an award called the Draper Prize, which is given for the advancement of engineering and education of public about engineering. And then also 5 years later, in 2019, three of the above mentioned were recognized for the Nobel Prize in Chemistry, which is a pretty awesome honor for anybody that's a nerd. So probably wondering what a battery consists of. I mean, we use them all the time, right? Well, there's two sides to it, the electrodes, and it's where the electricity either enters or leaves the circuit. There's an anode, which is the negative side of the battery, and then the cathode, which is the positive side. Here's a better picture. You also have a separator, which divides the sides of the electrolytes and of the electrolytes themselves, and then also the casing. So when it's discharging, you'll see that the electrons move in a certain direction from negative to positive, and as that's happening, the ions inside the electrolytes are drawn towards the electrons, and they're the only thing that can really move through the electrolyte. And then when it's charging, it's going in the opposite direction, causing the ions to go back. Here's an animation to make it a little bit easier. So it's what your EVs are doing when you're out driving. They discharge, all the ions go to one side. And then as it's charging at the station while you're feeding your faces for lunch, it's going to the other side. And then lithium battery chemistry, there's a lot out on the market, and It depends on what it's being used for. Like this first one, the lithium cobalt oxide, is used a lot in mobile phones, laptops, and digital cameras. The manganese oxide is used in power tools, medical instruments, hybrid and electric vehicles. The iron phosphates are used for forklift, weather monitoring devices, ocean buoys. You got manganese cobalt oxide, or NMC, which is used for power tools, e-bikes, and other powertrains, and cobalt aluminum oxide used in medical devices, industrial use, and electric powertrains. And the funny thing is, there's a laundry list of different lithium chemistries in batteries, um, and I didn't want to like list them all because it's a lot. So what I want to really talk to you about is the safety part of it, and like failure prevention when you take on owning lithium batteries, which we all kind of do with our cell phones and everything, but mainly the larger ones, like Paula just created a drone program, so we have these really large lithium batteries, and handling them is a priority to not burn our office down. But failure prevention, so when you're going out and shopping for these batteries, you want to make sure that you're you're buying batteries that are quality. What I mean by that, you'll find markings on the batteries, like this one's like the Underwriters Laboratory. They they test the batteries to make sure that they're safe. This is one of their symbols that they use, called the Recognized Component Mark. There's also like the Canadian Standards Association, and then there's also CE, which is what the European Commission describes as a passport that allows manufacturers to circulate products freely within the internal market of the European Union. But that, and then also properly storing the batteries is important. Um, if you know how dangerous the chemistry is, you have a whole new respect for it on how to store them. You don't want to put it by a bunch of flammable stuff when you're away from the house. Um, and here's like oh geez, I jumped the gun here. Sorry. Uh, and then if you have like a battery that needs to be replaced, it's good to make sure that you're replacing it with the right type of battery. Um, Hooking up a battery with wrong voltage can lead to damaging the electronic devices or damaging the battery itself. You never want to overcharge a battery, and once the battery is fully charged, you want to remove it, because all cells on the market have a different voltage range based on their chemistry. Be sure to stay within that range, and it'll prevent the batteries from having what they call runaway. When storing, make sure they are safely stored. Um, so, like you want to keep them in a dry, cool location, and like I said, away from flammables. And you definitely want to handle them with care. Don't abusively handle batteries. Damage to the casing can cause the battery to swell and create a fire. And when you do have damaged batteries, don't hang on to them. I know they're costly, but it's much safer to replace them and to make sure that the batteries are properly disposed of with your local recycler or battery store. Um, DOT has kits that for handling defective or damaged batteries, so that you can transport them with some safety. This next slide, it's DDR kit. It's a metal receptacle with a fireproof medium to bury the battery in while transporting it. So if the battery does ignite, it's not catching everything around it on fire. And this other picture on the right, this shows a soft fire retardant case using vermiculite as a fire safe medium. Um, at Paula, we're using a metal container. It's a thick gauge metal container, and we've lined it with fireproof filters and medium. Um, and this gives us more control to handle emergency situations. So here's one that we use to transport the batteries out in the field when we're flying our drone. And then this is our charging vault. So when we're charging the batteries, if anything happens, we're able to take this whole cart and go right out the door with it. And then there's also some carbon filters in place so that if it does smoke, we're not breathing a ton of it when it first happens. Identifying damaged lithium batteries. Defective batteries, they pose a thermal risk and the deterioration of the mechanical integrity. So it's best to inspect your batteries visually and test them with proper equipment, like a voltage or capacity tester. And then upon identifying damaged cells, be sure to remove from rotation, store them in the appropriate receptacle for transport, and take them to the proper facility for recycle, and then purchase a new battery. So because recycling is so important in our field here, I want to share a quick video. Oh, it's actually like a 12-minute video, but this is the part where it's not going to get boring for you. Yes. Oops. Switch screens here. 1 second. This video's from a gentleman named Matt Farrel. He runs a channel. He's a tech enthusiast, and he talks about sustainability and smart technologies, how they impact our lives. And let's see if I can get to his video here. Okay. This is it.
Between our obsession with mobile
Can you guys hear
electronics
that?
and the growing popularity
Yes, sir.
of vehicles,
Okay.
lithium-ion battery demand is growing at an astonishing rate. Most of that demand is being driven by automotive sales, which consume 60% of lithium-ion batteries, even though they only account for about 1% of automotive sales. It's not hard to imagine how far that's going to go in time, which raises the big question, what happens to all those batteries when they die? I'm Matt Farrel. Welcome to Undecided. I don't know about you, but I use rechargeable lithium-ion batteries for pretty much everything around my house. But when they no longer hold a charge, it's not always clear how to dispose of them. The same is true for old mobile phones, laptops, or tablets. You can sometimes find recycling containers at some big box stores, but it's not always apparent if they'll actually take the device that you're trying to get rid of, so it's not exactly an easy or frictionless user experience to recycle old lithium-ion batteries. And this is just consumer electronics I'm talking about. When you add the scale of electric vehicles, home batteries like Tesla's Powerwall, or grid-scale energy storage systems, the scope of the problem gets dramatically bigger. In 2015, lithium-ion battery demand was about 60 gigawatt hours, but just 5 years later had ballooned to 300 gigawatt hours. And according to some projections, it's expected to hit over 2 terawatt hours by 2030, which includes everything from consumer electronics to transportation. If you're talking about just transportation, the same report suggests that it will make up about 1.8 terawatt hours of that demand, which raises another question. Do we have enough materials to support that amount of battery production? The most common materials needed for lithium-ion batteries are nickel, cobalt, lithium, graphite, and copper. Just the demand for lithium alone is expected to grow from about 300,000 metric tons in 2020 to over 1.7 million metric tons in 2030. And while there are technically enough resources to support the demand, there aren't enough mines to dig it up and process it, and just adding mines alone isn't the answer, which brings us to recycling. Now, there's a common refrain that I hear from electric vehicle skeptics all the time. There's no way to recycle the batteries, which is just not true. In fact, there's a mad dash of companies all racing to corner the market for lithium-ion battery recycling. There are around 100 companies worldwide and dozens in the US and Europe alone that are all coming at the problem with unique techniques and technologies. Companies like Umicore, Neometals Limited, Glencore, Li-Cycle, and Redwood Materials. A common approach to recycling batteries is to have a spoken hub model. This is when a company has multiple locations that are set up for processing spent lithium-ion cells. They'll make sure that they're safely discharged and that they're ground up and processed into a black mass, which means they've removed things like plastics, copper, and aluminum. The remaining mixture is made up of things like lithium, manganese, and cobalt. It looks just like it sounds. It's a black mass of battery parts. That's transferred to a centralized hub facility that then processes the black mass to convert it back into its component parts. There's a lot of nuance to how this is done, but there are two overarching methods: hydrometallurgy, which uses chemicals, or pyrometallurgy, which uses high heat. I had a chance to talk to Zarko Maselgia, who's the CTO of American Manganese, which has a novel approach to lithium-ion battery recycling. In this case of American Manganese's recyclical process, it's hydrometallurgy.
We use just hydrometallurgy, so there's no high heat in the process. But then again, you have a hydrometallurgical process, but there is different techniques in the hydrometallurgy, like what chemical reagents you use in it. So hydrometallurgy is a general term, but how it's done is, that's within our patents as well.
So when you're talking about chemicals, concerns come up around worker safety and how environmentally safe it is. In this case, it's very safe, and the process itself is kind of recyclable.
So with our process, we've developed a closed circuit or locked cycle process where the solution from the end of the process is cycled back within the process. So you don't have any harmful environmental discharge. It's within the contained working area as well. You are dealing with these chemical reagents, so there is a level of know-how and how to handle those materials.
So what does this process actually look like? Well, Zarco was kind enough to walk me through their test facility, which looked a lot like I imagined. Kind of a big chemistry set. It all starts with the scrap or black mass. Now, on this issue of scrap, that's American Manganese's initial focus. As an example, when a typical cylindrical style cell is manufactured, they're coating cathode and anode layers onto foil sheets and then rolling them up. I mean, it's oversimplified, but in a nutshell, that's what's happening. There are parts of that are trimmed off during the manufacturing process, cells that don't pass quality assurance testing, a whole host of reasons that manufacturing defects occur, which creates a lot of wasted material. A good example is to look at how much cell production that Tesla and Panasonic were having to scrap during the initial stages of the Model 3 production ramp-up. An average of 39% quarterly cell loss. They were essentially having to throw away 3 to 4 cells for every 10 that they made. Recovering that scrap and processing it so that they can go back into the manufacturing cycle can save a lot of money and resources. Zarco showed me some of the cathode scrap they sourced from third parties.
You see some of them big chunks. You can cut this down. I guess you call it shredding as well, but not shredding a whole battery. Because then you have a very pure product. There's no more. It's essentially your base metals. You have your lithium and aluminum, and then PVDF. So maybe you have some small percentage of plastics. What you see, like in this tank, for instance, those foils would go in, and we would cut them up into kind of those little tinier pieces to just allow for better mixing. Then the reagents we use would separate that active material from the aluminum foil. And essentially what you would produce from that then, you're pretty much pulling those metals into solution. And here you would have what would be the pregnant leach solution. So essentially in these, if I can remember correctly, I think this would be the NMC. But in this solution, this is your nickel, manganese, cobalt, lithium, and you may have some other impurities as well.
After that, the materials are co-precipitated out, which is a process for separating a solid from a solution. When everything is complete, you'll have clean aluminum and foil scrap.
From the trimmings, we separate active material to the aluminum foil. Then we leach that active material into solution. And then what we pull out first, in this case, let's say this is an NCA. In here would be, lithium, nickel, cobalt, maybe some impurities. Filter out the impurities, and then precipitate out nickel and cobalt together, the hydroxide. And then what's left in that solution is lithium, which we also recover, and we can recover as a carbonate or a hydroxide. Yeah, and then when you see the bags of material we've produced, this is a nickel cobalt carbonate, and this is a hydroxide. Really, the difference is what reagents we're using in that precipitation. So there was a few trials of different materials.
What sets apart American Manganese's approach to recycling is how they're trying to vertically integrate the process into existing battery manufacturing facilities. Instead of the spoke and hub model, they're working closely with battery manufacturers to custom tailor the recycling process to end up with a usable cathode mix for producing new cells based on that manufacturer's needs. Each company has very specific chemistry mixes for their cathodes, different amounts of nickel, cobalt, lithium, different particle sizes, shapes, and densities that are needed. So the final cathode precursor that they can deliver cuts out a refinement step that's typically needed from other recycling approaches that you might see with spoke and hub.
You have the different compositions of nickel, manganese, and cobalt, and the approach of working more so directly with a cathode manufacturer or battery manufacturer is that one, your feedstock is homogeneous, and then the material can be directly integrated more so than sold to an independent recycler, which then sells that into kind of midstream within the lithium-ion battery market, only to be further refined and processed.
That tight integration with dealing with scrap loss can have a big impact on driving down costs, especially when you consider how much of the materials they can recover.
From lab tests and our pilot plant tests, within our patent, we've achieved up to 100% of lithium, nickel, manganese, cobalt, aluminum. We've scaled up to a pilot plant test, and some of our extraction results in the pre-leach and leach was 99.7%, and then that's with high purity as well.
There's also the transportation of materials and finished batteries to consider too. Currently, the majority of lithium-ion manufacturing is in China and the United States, but China dominates with over 80% of global production. The United States is about 8%, which is primarily from Tesla. But the materials like lithium come mostly from Australia and Chile. And recycling batteries closer to the locations where they'll actually be manufactured will save significantly there as well.
You're crossing multiple continents by the time it actually gets into a lithium-ion battery. You reduce on transportation costs, and then the material as well is very pure. When you're mining things, for some deposits, 30% that grade is an amazing thing, but what do you do with the 17% waste? So there's those things aren't considered.
Reducing transportation and higher grade materials that are ready for new manufacturing sounds like a step in the right direction. So what's the holdup? Why isn't this standard operating procedure yet? Well, these things take time. Whenever I've talked to anyone in the field like this, a common theme always comes up. It takes a lot of time to go from bench research to test facility to demonstrator plant to full-scale production. Many of the recycling companies out there are somewhere around the pilot plant and demonstrator plant phase of this rollout.
And now with this demonstration, it's going to be an upgrade or a scale up of that pilot plant to a 500 kilogram per day capacity. But now each of those stages will just all be integrated in one and ran continuously over a few weeks. And from there, we'll be able to pull engineering data, economic data to put forward into a design for commercialization. So each step of the way is de-risking the process.
Li-Cycle, which is another leader in the space, has been building out a spoke and hub network. They already operate a demonstrator plant in Kingston, Canada, and it's building out another facility in Rochester, New York, my old stomping grounds, in an old Eastman Kodak building. That's supposed to be open in 2022, and they just recently announced another facility in Arizona. And I can't not mention former Tesla co-founder J.B. Straubel's Redwood Materials. They've been making a bit of a splash recently for obvious reasons. J.B. Straubel is intimately aware of the intricacies and challenges ahead of us with lithium-ion batteries. Their initial facility is able to recover about 80% of a battery's lithium and up to 95% of other materials. And they're already profitable at the unit level. According to one report, the battery recycling market is expected to grow from $1.5 billion in 2019 to $12.2 billion in 2025 and $18.1 billion in 2030. That's definitely good growth potential, but not the scale that we need to match the battery demand growth rate. We're just at the tip of the iceberg here. And while recycling will be essential for sustainability and meeting demand, it's most likely not going to replace mining completely.
I don't think recycling will completely replace mining anytime soon. I think it'll complement the supply chain, but I think we're going to need both for the near future at least.
So what do you think? Will recycling overtake the need for mining? Jump into the comments and let me know.
All right, so let me switch out here. Find out where my tab is. You guys still there with me?
Are here.
All right. Yeah, this Excel events is pretty fun. So you guys see my screen here?
Yep.
All right. So yeah, it's something hopeful to think about, with the recycling. But let me go into identifying your. Oh, we already did that. Let me go a little bit further. I got a couple more videos, but these ones are really short. So let me get back here. I told you I was going to make it fun. Where's that? It's pretty tricky to learn how to use all this.
You're doing fine.
Okay. Here it is. So you guys should be able to see this. I think the video.
That's right.
Play
Just
this.
like a tank of gas, just like a tank of gasoline or a bullet in a gun, a battery has a lot of energy in it. And if that energy is released in a way that we don't want it to be released, a fire can occur or even an explosion. Nowadays, lithium-ion batteries are used in pretty much everything from children's toys to laptop computers, our cell phones, power tools, and even some vehicles. If there was a simple way to describe why a battery would catch fire and explode, there'd be a simple way to prevent it from happening. There's a lot of pieces and processes that go into making the battery work. If any of those processes go wrong, there's a chance for energy to be released. And the reason that happens really is because the electrolyte inside of the battery is an organic solvent, and that solvent is flammable. So if the battery can't vent, you build up pressure as the electrolyte burns, and then it explodes. Thousands of these things are being made per hour, if not hundreds of thousands. And in that mass production process, if something goes wrong even a little bit, it might be very difficult to catch, but small mistakes lead to big problems down the line. In previous instances of batteries catching fire, the cause has been bad welds. A lot of the pieces of the battery are welded together, and if you don't have a good weld, you develop resistance. The resistance develops heat. Heat leads to fire. Other times it has been because of contaminants during the building process. Contaminants were generated, a little bit of metal scraped inside of a machine, and that contaminant fell into the cell, and that caused a hard short between the anode and the cathode, which then generated heat, and so on and so forth. Generally, there's lots of different approaches that are being looked at on ways to make batteries safer. Really, the cutting edge approach, what's being looked at here on campus, is an all solid state electrolyte. So we would remove the flammable liquid entirely from the cell and just put down a ceramic layer that is capable of conducting lithium ions but not electrons, to allow the anode and cathode to talk to each other in a way that is functional and not going to short out the cell. You know, there are lithium ion batteries everywhere around us all of the time, and the vast majority of cases, nothing goes wrong. A battery is stored energy. Whenever you have stored energy, there's the potential for that energy to be released in a way that we don't want it to be. Accidents do happen, but to combat that, there are professors here on campus, including Dr. Sakamoto and Dr. Dasgupta, who are looking at different ways to make batteries and make them safer for future use.
All right, so I have to share that with you there. And then I got one other video I'd like to share before I move into some more lecture here. Pull it up. So yeah, he was talking about how it can be very unstable. So I want to share, this is some footage. It's a thermal imaging of a battery doing what they call Runway. And this pack is like designed so that it could produce more voltage or more capacity. So there's other batteries with it. And unfortunately, when one goes bad, it affects the rest of the batteries in the pack, and it becomes very dangerous. Okay. So you guys got to see that. Let's move forward here. There it is. You guys see it again? All right.
Yep.
Okay, so that was some videos on thermal runway, which is one of the dangerous parts of the lithium chemistry. And it's funny because like this next slide here shows a DARPA's RoboSimeon. This was like done in NASA's Jet Propulsion Lab, and this was back in 2016. Yeah, so it wasn't that long ago. But at the time when they were working on this project, they didn't know how to deal with lithium chemistry in the event of an emergency, and so one of the engineers or techs that was charging this forgot a safety protocol during the charge, and this thing had like a 96-volt battery in it, and it took off. I have another video of that, but I don't know if I have too much more time. Actually, let me see if I can share it real quick.
There's always time to see video of things exploding.
Okay. Yeah. I said I was gonna make it fun, right? Okay. Let's find that one. Here we go. Woohoo! So yeah, this is NASA, right? They should know everything. Let's see, we got 3 minutes on this video. I think that'll be fine. So there's all the brainiacs. You're seeing this okay, Shasta?
Yes.
Okay. So here it is. Keep your eyes peeled.
Dude.
It's incredible to see something like that up close. It's pretty darn scary. Now, he's using a fire extinguisher that is not set up to deal with lithium ion fire. Fire extinguisher number 2. The funny thing is, though, like even though he suppressed it, the chemical reaction is still going on. It's like those birthday candles that don't go out. And I think they eventually bring in their fire crew to take care of it. Yep, see, there goes. Happy birthday to you. Yeah, I hope I don't have to pay royalties for that one. So yeah, in a nutshell, that's pretty much it. I think they fast forwarded these guys making the same mistakes with the fire extinguisher, and they eventually just take it outside.
I shouldn't be laughing, but I'm sorry. It is kind of comical.
It is. And, I mean, it's NASA. It's like, come on, really, you guys are the geniuses. How many NASA scientists does it take to blow out candles on a birthday cake? Okay, so I think you guys get the gist of that. Let me go ahead and go back here. Where's my slideshow? Getting used to this accelerants thing here. There we go. Okay, you guys can see my slideshow again, right?
Yes.
So yeah, that was the whole NASA incident. But yeah, they obviously weren't prepared for what that is, and fortunately now they have new policies in place for safety, so that doesn't repeat itself. Let's see. So thermal runaway and handling of lithium fire. It's hard to determine if like something is happening internally in the battery. I mean, we do have like hints where the battery might swell or something. You can actively see that. But you know, in that event, you have such a limited amount of time to deal with it and keep it from going any further, like burning down a building. So I always recommend, like, if you're like going out flying drones or something, you got some pretty large batteries, have like a metal receptacle with you that has like some sort of medium in it, like some playground sand or vermiculite, which can be bought in like the gardening section of your big box stores, or a properly rated fire extinguisher. Class D is what's used for metal fires. And never ever use water to try and put out a lithium fire. Lithium is violently reactive with water. And I have another video for that too. Let's see here. Like Shasta said, the videos make it great. So here we go. This one's a real quick one. So we got our little flask here. So you can see the lithium's kind of bubbling, looking like Alka-Seltzer. But give it a moment here. A lot of the stuff that it's off-gassing is pretty darn flammable. So it's doing it's an endothermic reaction, building up some heat. Pretty cool though. When it takes off, it takes off. Yeah, I wouldn't touch that. Almost looks like it like melted the glass there, which I wouldn't doubt it. Let's see, back to our slides here. Getting better here. Alrighty. So,
Yeah, we're having a lot of comments here about people having some of their own experiences with batteries swelling. So
oh
this
yeah,
is good.
And you know, like I said, you with how dangerous this chemistry is. It's important to know how to deal with it. You know, have some type of emergency plan. So thermal runaway, you've heard it talked about. What it actually is inside the battery chemistry itself, in the electrolyte and the anodes, or the anode, sorry, you get these what they call dendrites that form over a period of time, and eventually they kind of look like stalagmites or stalactites. They'll actually go and start to pierce through the separator layer, causing a connection between the anode and the cathode, which will create heat and it's an instant short in the battery, and then causes the battery to swell, flame, and do all that horrible stuff. From my experience using lithium batteries, this can be minimized. I wouldn't say it can be eliminated, but usually this happens when people kind of abuse the use of their batteries, like run the battery all the way till it doesn't work anymore, and then throw it on the charger and keep doing it over and over again, and hitting the absolute limits of its voltage capacities. That's it's a bit much, and it's pretty abusive on the chemistry inside the battery. So I do have recommendations of. So the thermal runaway common damages, like mechanical, like if the separator's torn, electrical, the separator's pierced, or thermal abuse where like it collapsed. But yeah, it all leads to an internal short in the battery and fire and explosion and smoke and all that wonderful stuff. Let's see here. So, before I go into this slide, because it's the future. So when I was telling you that different chemistries have different voltages and stuff, share my mug here. So like in front of me here. I have this. This is a drone battery that we use on a smaller drone that we have. Comparable to this, like our other drone that uses a battery that's like, it looks like a brick. Um, and generally, like there'll be a voltage limit on that chemistry. Like ours is the voltage limit's 4.2 volts. Um, just when when you're using something where you have control over the charging limits, you never want to go to the peak. Instead of going to 4.2 volts, I would try to charge it to like 4 volts or 4.1. I always want to stay under that, and then I would never run it out completely. You can hook little testers up and see where your voltage is at, and if it starts getting pretty low, like then you do want to like change it out and put a different battery in, and let that one rest, because if you're using it, it's probably got a little bit of warmth to it. So yeah, it's just it's pretty basic, and it's the same that they do with the EV cars. Like they'll have a board in place. It's a battery management board that controls its charging and discharging. It'll never go to its outer limits. It'll always stay in between, and with a lot of cushion, and it actually prolongs the life of the battery. Like where they say a battery is going to last 3 years. If you actually do this, you can actually probably get an extra 2 years out of it. So just something to think about. But the future of batteries, this is kind of interesting. So there was a gal at the University of California, Irvine, who came up with what they call a nanowire battery. And this was like thin strands of gold used. The problem was when they started testing it, the strands were so fragile they were breaking. So she used like a gel, like plexiglass electrolyte encasement around the fibers, and it actually they were able to do like, I think it was 200,000 charge cycles on this. Usually a regular battery, you're lucky to get like 6,000 to 7,000. So it's like the forever battery. But you know, the price of gold and stuff, I doubt this is like the way we'll be going in the future. But it's nice to know that there's options out there, you know, for more research to be done. IBM has a technology that they introduced a while back, using an air breathing battery. With the amount of time we have, I'm not going to go into a video for that. But I will say it's pretty interesting, and I will share like some links with you guys for those who are interested on doing a little bit more. Solid state batteries. So this, I think, it was talked about in the Michigan, Greg Les, that video I showed you. This is where they're taking out the liquid electrolyte and replacing it with like, so they're using this solid layer, which allows the lithium ions to travel through it, but it doesn't allow these dendrites to go through it. The dendrites are that's a picture under a microscope off to the very right there of dendrites forming in a cell. So other chemistries that we got right around the corner and technologies, graphene aluminum oxide, which has been talked about with, I think General Motors released a commercial on one of its upcoming phases for their EV market. And it's supposed to dramatically increase driving range, possibly doubling what we're seeing today. And the charging would be like 60 times faster. Then the carbon nanotube technology for electrodes, for ultra fast electrodes is what they're calling it. And it's basically allowing a lot more surface area for electrons to travel. Cobalt free. So they're trying to use like silicon anodes, which be like glass or glass ceramic structures. The cool thing about this, like phasing out cobalt, I mean, right now there's like human right issues with cobalt mining out in Africa, and it's really expensive because it's not found everywhere in the world. So this would be very cost effective for the market to find an alternative to that. And then land mining. I mean, there's more lithium that they discovered in the ocean than there is on land. In fact, there's probably an infinite quantity of lithium out in the ocean. The reason why they weren't mining it out in the ocean is because they didn't know how. But recently, they've figured it out. A lot of the scientists getting together figured a way of like pulling and extracting the lithium from salt water and getting pure lithium out of it. And it's 500 times more lithium than what's on land, or not 500, 5,000. So that this is like things to look forward to, and it's going to help our environment a lot by going this route. So that's pretty much it in a nutshell there. Sorry, I went over a little bit on my time. But please, if you have any questions or comments, let me know. I'd be happy to try and answer them to the best of my knowledge. And thank you, Shasta, for helping me out here. She's
You're welcome.
Very helpful during this whole conference. She deserves a big pat on the back.
Donuts. Send donuts.
Donuts. She likes donuts.
All right, I'm going to go ahead and stop the broadcast here, and we got you guys got 5 minutes to get to 11 o'clock sessions.
Okay.
And thanks, Darold. That was great.
Yeah, keep my contact info if you guys want to hit me up, or hit me up in the conference here. I think you can like message me directly.
Yeah.
If you have any questions, I can talk about our drone program as well.
All right. Bye, everybody.
Take care.